My name is Lucia Bellino, and I will be presenting my senior honors thesis called Presence of Hydrothermal Mineral Alteration in the Iradania Basin on Mars, Implication for Serpentinization, Habitability, and Magnetization. There's a plethora of evidence to support the theory that liquid water existed on Mars during the Noachian 3.5 to 4.1 billion years ago. Most Noachian terrain is in the southern hemisphere of Mars, as pictured in image B here. The Noachian terrain is the blue terrain. And within the Noachian terrain, we've detected conglomerates, as pictured in image C, as well as extensive dendritic valley networks and crater lakes. You can see these in images D, E, and F. In image D, we have an analog to the terrestrial delta. This is actually where the Mars Perseverance rover landed. And so in addition to all of this, we've also been able to detect hydrated minerals on Mars using spectroscopy. So with all of this evidence, it's pretty compelling that there was liquid water on Mars during the Noachian. But this kind of unlocks a mystery about how liquid water could have existed on Mars during the Noachian, because 4 billion years ago, the sun's luminosity would have been 20 to 30% weaker than it is today, and Mars receives 57% less solar radiation than Earth does. So how could Mars have achieved temperatures warm enough to support liquid water on the surface? The first idea that kind of came about was that Mars would have had a really thick CO2 atmosphere. And theoretically, the CO2 atmosphere would have been so dense that it would have caused a greenhouse effect that would have allowed a temperature that was warm enough for liquid water to be sustained on the surface. And if we would have had a really dense CO2 atmosphere, in addition to having liquid water present all over Mars, then we should see carbonates distributed widely throughout the planet. And even though we've been able to detect some carbonates, we have not detected them to the extent where you could conclude that there was a dense CO2 atmosphere. Furthermore, we've now created models of the atmosphere of Mars during the Noachian. We've saturated the atmosphere with CO2 and H2O. And even when you've saturated the atmosphere so much that CO2 is literally precipitating out in these models, it still is not enough of a greenhouse effect to allow the presence of liquid water on the surface of Mars. And so from this evidence, two different climate models of Mars during the Noachian emerged. On the left side, we have a much warmer and wetter version of Mars. So even though the greenhouse effect that would have been produced by CO2 would not have been enough to sustain liquid water on the surface, if you look to more exotic greenhouse gases like SO2 or methane or H2, they could have produced a greenhouse effect that would have been large enough to support the presence of liquid water. And these different gases could have been released from events like outgassing, volcanism, or impacts. On the right side, we have the other climate model of a much colder, icier Mars. And as you can see, all this white here is where there would have been ice sheets on Mars. So instead of having liquid water visible on the surface of Mars, we actually would have had the geothermal internal heat of Mars inducing basal melting or melting of the bases of these ice sheets, so that a lot of the water features that we've viewed on Mars today would have actually been produced underneath of these ice sheets. And so the hydrous minerals that we've observed on Mars would have actually been produced in the subsurface and then would have later been exposed. One region that's really interesting to study, both for climatic implications as well as many other factors, is the Iradania region. For some context, the Iradania region is located on the boundary of Terra Sirenum and Terra Samaria, and it's this region that's made of a bunch of interconnected basins. There is a bunch of evidence within this region to support the idea that the region was once ice-covered sea. And so there are scarp-bounded benches and Gorgonite chaos. There's concave hypsometry of the basins, and there's also the presence of iron-rich minerals throughout the region.
End of the cruise, actually probably, extending like a month.
So all of this evidence points
everybody
the idea that this has been
if they're working.
All this evidence points to the idea that the Iradania region would have been an ice-covered sea. And so there are iron-rich minerals that would have indicated a really reducing environment of the region, in addition to scarp-bounded benches and concave hypsometry of these basins. So on this figure on the right here, you can see the Iradania region marked here. This is an elevation map, so areas with lower elevation are in blue and purple, and areas in higher elevation are marked in red and orange. And so a lot of these regions with lower elevation are located within the Iradania region because they're basins. We also have a contour surrounding the Iradania region, marking 1,100 meters, as well as a 700-meter contour in white. We have deep basin deposits indicated by this black and white stripe pattern, as well as Gusev Crater and Madame Wallace that are marked in this map because Gusev Crater is one of the craters that a Mars rover visited, and Madame Wallace is the major channel that drains into that crater. So Mikulski et al., who produced that figure, also calculated the amount of water that would have been contained within this hypothetical Iridania Sea. And they found that the amount of water that would have been contained in this Iridania Sea would have been more than all of the rest of the liquid water on Mars combined. It also would have been about 3 times the amount of water that's contained in the largest landlocked sea on Earth, which is the Caspian Sea, and it definitely would have far exceeded any amount of water that's found in any of the lakes on Earth. And so this would have been this huge reservoir of water on Mars. So you'd expect to see a lot of minerals that are hydrated and contain H2O within their molecular structures. Mikulski further examined this by using spectroscopy to detect different hydrated minerals in the region. He was able to find smectites, jarosites, serpentine, dolomite, and agarite. If you look on the right here, we have another elevation map with the major basins of the Iradania region marked. And we can see all of the different minerals that have been detected in the region, from chlorides to magnesium and iron clays to carbonates and jarosites. Mikulski, as I said before, had detected serpentine, and I was particularly interested in this detection of serpentine because of its astrobiological implications, which I will discuss later in the impacts of my project. The serpentine that he found was in Ariadne's coals over here. Now, despite all this evidence to support the Iridania region once being an ice-covered sea, the formation environment of this region is still debated. Leverington published a paper last year that actually argued that the Iridania region was formed from dry volcanism. And so this hypothesis came from 2 different threads of evidence. The first being the morphology of the region. And so Leverington claimed that the morphology of the region, especially the chaotic terrain within Gorgonam Chaos, was most closely similar to volcanic plains that are observed on Earth. The other thread of evidence that he looked at was the distribution of hydrated minerals that have been detected on Mars. So if you look at this figure here, we have the outline of the hypothetical Iridania Sea outlined in white, and then all of these red markers indicate detections of hydrated minerals. And so Leverington argues that these detections of hydrated minerals within the Iridania region are not statistically significantly different than detections of hydrated minerals outside of the region. And so you can't conclude that there would have been more water within this region that would have been an ice-covered sea based upon the detection of hydrated minerals. Furthermore, he also claims that some of the detections of minerals that people claim could be indicative of an ice-covered sea, like sulfides and chlorides, could have actually been formed by volcanic and magmatic processes. And so overall, the formation environment of the Iridania region has not been constrained. Another reason why this region is really interesting to examine is its enrichment of potassium and thorium. So if you look at this figure on the right here, the topmost figure shows the concentration of potassium throughout Mars. So regions of yellow and orange coloring are areas that contain much higher weight percentages of potassium, and areas that are blue or purple represent areas that have much lower percentages of potassium. And so these 4 triangles represent the 4 major lakes within the hypothetical Iridania region, or within the hypothetical Iridania Sea. And as you can see, these 4 basins fall within an area of higher concentration of potassium, which is a radioactive element. Similarly for thorium, again, thorium concentrations that are high are measured in or are marked by orange or yellow coloring, and concentrations that are lower are marked by purple or blue coloring, and the thorium is measured in parts per million. Again, these 4 major lakes of the Iridania Sea fall into an area that has a high concentration of thorium, which again is a radioactive element. It is notable that both of these are data derived from the gamma ray log spectrometer, and so it only reveals the topmost part of the crust, not the entire crust. And so Dr. Oja conducted a study in which he produced students' t-tests on the region to determine where, or on the map of Mars, to determine where areas with particularly high concentrations of potassium and thorium were located. And as you can see, the 4 major basins of the Iradania region fall into areas that have anomalously high values of potassium and thorium. And so when further calculating the crustal heat flow of the Iradania region during the Noachian from this radioactive decay of potassium and thorium, Dr. Ojha et al. Found that the crustal heat flow could have exceeded 45 milliwatts per meter squared just from the radioactive decay of potassium and thorium, so not including additional heat inputs like from impacts or from magmatic intrusions. And with a conservative mantle heat flow contribution of 20 milliwatts per meter squared, it could have actually surpassed 65 milliwatts per meter squared. And so this crustal heat flow would have been enough to support a hydrothermal system in the Iradania region during the Noachian. And furthermore, it would have actually supported temperatures at relatively shallow depths at which minerals like serpentine would have been able to form. So for my senior thesis, I sought to detect hydrothermal mineral alteration throughout the Iradania Basin in order to better characterize the formation environment of the region. The main instrument whose data I used in order to conduct my study was CRISM, which is the Compact Reconnaissance Imaging Spectrometer for Mars. This satellite has detectors in visible, infrared, and near-infrared wavelengths at 430 different band measurements. And so this satellite is able to take images of Mars terrain and determine where certain frequencies are absorbed more versus where they are reflected more. And this gives us information about the mineralogical composition of Mars. Because this is a satellite located at about an altitude of 300 kilometers, each pixel within each of these CRISM images represents about 18.4 meters of terrain. So in order to actually produce spectra for me to analyze, I first had to download these images, these CRISM images, and they're open access. So if any of you wanted to download them, you would be able to. I then used a software called ENVI to apply an atmospheric correction to minimize the effects of Mars' atmosphere. Because these images do not account for the curvature of the planet, I also used the ENVI software to map project each image. I then ran the images through a custom MATLAB algorithm in which each pixel was divided by the median pixel value in each column to try to minimize the noise that's visible within these spectra. I then was able to extract spectra from these atmospherically corrected, map projected, normalized images from interesting regions, and then finally compare these interesting spectra with Mars or with lab spectra in order to classify the mineralogy as probable serpentine, potential serpentine, or hydrous minerals. And so because we're looking at satellite samples from Mars that are each pixel represents around 18 meters of terrain. I'm looking at around 10 to 30 pixels to minimize the amount of noise that we're seeing. It's very unlikely that these exposures are 100% pure serpentine, even though our lab samples are completed in labs on Earth and they are 100% pure serpentine. And so our spectra from the lab or from the Mars samples are never going to completely match the lab spectra. However, I was able to classify the mineralogy as probable or potential serpentine or just hydrated minerals, depending on how closely it did match that of the lab spectra. And so in total, I analyzed 43 images and I focused on 2 different locations. First, I focused on Aramis Coves, which is where Mikulski was able to detect serpentine. So if you see on the map here, we have these black markers represent locations where Mikulski identified hydrous minerals. And then this is the images in which he was able to identify serpentine. I then looked at the images surrounding the image in which he was able to identify serpentine to see if I could find serpentine in this area as well. I was able to identify probable serpentine, potential serpentine, and hydrated minerals as indicated by the blue, red, and green markers respectively, as well as in the Gorgonam Chaos, which was one of the main regions that Leverington pointed to as containing terrain that morphologically indicated it would have been formed by dry volcanism. So I was able to detect probable, potential, and hydrated, or probable and potential serpentine, as well as hydrated minerals throughout the Iradania region using spectroscopy. So this is one of my instances of probable serpentine. On the left here, we have a normalized map projected atmospherically corrected CRISM image and the zoomed in region that I was looking at. So this spectra is produced from the 11 pixels that are highlighted here. This graph here shows on the y-axis relative reflectance, and the actual relative reflectance value does not matter because we are already ratioing the spectra in order to produce as little noise as possible. And so what really matters is that the minima in the absorption bands are at the wavelengths, which is what on the x-axis, that match those of the lab samples. And so on this image, we have two lab samples of serpentine in orange and black, and then my Mars sample in blue. And so serpentine contains 3 absorption bands that are characteristic of the mineral, and they indicate the different bonds that are present. And so the 1.93 micron band indicates the presence of bound water. The 2.315 micron band indicates the presence of a magnesium hydroxide bond, and there's also a 2.51 micron band. And so in order for an image to be classified as probable serpentine, it needed to clearly exhibit all 3 of these absorption bands. So you can see my Mars sample here clearly has the 1.93 absorption band, as well as the 2.315 and 2.51 micron absorption bands. It is notable that the spectra is a little bit noisy because they are satellite-derived data, but the absorption bands are very much present in the spectra, and so it was classified as a probable, as an instance of probable serpentine. This image was from Ariadne's coals, but I was also able to identify probable serpentine within Gorgonom chaos. So this is an image from Gorgonom chaos, and this is the spectra from this CRISM image. Again, you can see an absorption band at 1.93 microns, 2.315 microns, and 2.51 microns, all indicating this is also serpentine. Some images were more difficult to conclude that what I was seeing was actually serpentine because some images are noisier than others. And so in images in which I thought that I could see all 3 of these absorption bands present, but they were rather noisy, they were classified as potential serpentine. So for example, here in this image, we can see absorption bands at 1.93, 2.315, and 2.51 microns. However, there's a lot of noise in the spectra, and so it requires some further statistical analysis in order to ensure that what we're seeing at these absorption bands are actually absorption bands and not just noise. And I was also able to identify potential serpentine in Gorgonom chaos. So again, you can see here, the spectra is very noisy, but it does appear to have absorption bands at 1.93, 2.315, and 2.51 microns. Again, none of these spectra are going to perfectly match the lab spectra because we're likely not looking at 100% serpentine in these exposures on Mars. Of course, not every image that I looked at contains serpentine, but some just contain hydrated minerals. And so again, that 1.93 micron band is indicative of bound water. And so if minerals had, or images had those 1.93 micron bands, then it was, I classified it as just a hydrated mineral. So for example, the spectra contains the 1.93 micron band and a 2.315 micron band, but no 2.51 micron band. So it's definitely not serpentine, but it does contain the 2.3 micron band that indicates magnesium hydroxide bond, and the 1.93 micron band indicating the presence of bound water. So it could, for example, be a magnesium smectite or some other kind of mineral that contained both magnesium and water. Here's another example of a hydrated mineral, again containing the 1.93 micron band and the 2.315 micron band, but missing the 2.51 micron band, indicating a hydrous mineral that contains magnesium, but not serpentine. So in conclusion, I was able to detect serpentine in hydrated minerals throughout the Iradania region in both Ariadne's coals and Gorgonom chaos, and this was the first time that serpentine has been detected within Gorgonom chaos. And this supports the theory of a hydrothermal system in the Iradania region and the Iradania region once being an ice-covered sea. This has some really interesting applications because serpentinization produces hydrogen gas, which can be used metabolically in some microbes, as well as serpentinization producing magnetite as a byproduct, indicating that some of the magnetization observed in the Iradania region could have been influenced by serpentinization. So to discuss serpentinization further, this is a pressure temperature stability diagram. And so here we have, by the dashed lines, we have different thermal gradients, and then we have the thermodynamic equilibrium of different ultramafic mineral and water interactions. We then have the minerals that would be present if you were to hypothetically drill a huge core into Mars' surface. What you would have would be brucite and crystallite on the top, and crystallite is one of the low pressure, low temperature forms of serpentine. And this is for a thermal gradient of 16.5 Kelvin per kilometer. So Dr. Oja's research on the rate of decay of potassium and thorium in the region indicates that temperatures would have been achieved that could have produced crystallite at relatively low depths. This has some serious implications for habitability because serpentinization produces the conditions, chemistry, and mineralogy that are potentially related to the origin of life. And furthermore, if we look to Earth, there are microbial communities on Earth, such as the Lost City, that are able to thrive only off of the products of serpentinization because serpentinization produces H2 gas as a byproduct. And so these microbes are able to utilize the H2 gas metabolically and do not require any additional energy input, for example, volcanism. Additionally, there was a study that was produced earlier this year by Tarnas et al. That looked at the implications for sulfides producing sulfates and those having a connection to habitable environments on Mars. So serpentinization produces a really reducing environment, which can cause the precipitation of sulfides. And we can see this in the section 3 of this image that has a hydrothermal sulfide with serpentine. And so regions with serpentine could have created hot zones for ancient cumulotrophic life that consumed both hydrogen gas and sulfate gas because due to radiolysis caused by serpentinization, in addition to H2 gas being produced, it also could have created sulfate gas from the sulfides that had been precipitated out in this region. And so different microbes could have survived in these regions and used both the hydrogen gas and the sulfate use them metabolically, creating potentially habitable environments on Mars. Furthermore, serpentinization also has implications for magnetization. So in this figure here, we are looking at a map of Mars with the magnetic field on top of it. And so we have areas with very low magnetic fields in blue and areas with much higher magnetic fields in red. So the Iradania region falls around here. And as you can see, it has a very red high magnetic field. In the first image here, we have the different dendritic valley networks mapped out on top of this magnetic map. In the second image, we have the presence of chlorides, phyllosilicates, and carbonates mapped out over top of this magnetic map. And then in the third image, we have different craters and volcanic landforms mapped out on top of this volcanic map. So a lot of times when we view a magnetic field on a planet, we assume that all it's showing is the thermal remnant magnetization. So the last time those rocks cooled beyond their Curie temperature, they just recorded that magnetic field at the time and then they were done. However, serpentinization produces magnetite as another byproduct, and magnetite can record the magnetic signal when it was formed. And so there could also be chemical remnant magnetization occurring when this magnetite was forming from serpentinization. So some of this magnetic field that's observed in the Iradania region might not only be thermal remnant magnetization, but also chemical remnant magnetization caused by serpentinization. Of course, we don't see serpentine like widely distributed throughout the surface because it would have to be excavated kilometers to the surface and then exposed. But serpentine and serpentinization causes a lower density, a lower crustal density than the average crustal density of Mars. So on this map here, we have the density of Mars mapped out. So areas in blue are lower crustal densities, whereas areas in red are higher crustal densities. Again, the Iradania region falls here in an area with a lower crustal density. On this map up here, we have the dendritic valley networks, and then on the map down here, we have chlorides, phyllosilicates, and carbonates mapped out on top of this density map. And so the Iradania region falls here, where there are a lot of detections of different hydrated minerals in an area of low density. So it suggests that in the subsurface, there might have been a lot of serpentinization that would have caused there to be a lower density, and therefore also the serpentinization would have also impacted the chemical remnant magnetization that is observed in the region. So in conclusion, I was able to detect serpentine throughout the Iradania region, and this supports the Iradania region having a formation environment as an ice-covered sea and furthermore as a hydrothermal system. And this really is important because further than just being, or in Leverington's paper, he explicitly points out Gordom's chaos as having terrain that really resembled volcanic plains on Earth, but I was actually able to detect serpentine within Gorgordon chaos for the first time, which goes directly against the hypothesis of only having dry volcanism as the formation environment. The serpentinization is also really important because it potentially has implications for astrobiology and could have provided the conditions and products such as hydrogen gas that would have allowed microbes to survive in the region. Additionally, serpentinization could have potentially contributed to the chemical remnant magnetization by producing magnetite as a byproduct that is observed within the Iradania region. In the future, I'm hoping to really increase the number of images that I examine because there's still hundreds of more images within the Iradania region to explore. And I'm hoping to expand the region of interest beyond just Gorgonophaeus and Ariadnes coals and to other regions of the Iradania basin in which hydrothermal minerals, especially serpentine, have never been found before. I'm also hoping to conduct statistical analyses of the plots that I produce in order to determine or in order to confirm that the classifications of potential serpentine, probable serpentine, and hydrated minerals that I classified them are correct. And I'm hoping that with this future research I'll really be able to further constrain the formation environment of the Iradania region and rewrite the context as we currently know it. Thank you.
Hey, awesome. Thank you. You want to unmute yourself and give a round of applause to Lucia. And I'll try to be a moderator here and take any questions you may have for Lucia. You can either type it or just unmute yourself.